All right, everyone. I know I have some questions over the homework, which is fine. But before that, I promised you I would come around and I would check your homework for 2 quiz grades today. So as we did before, take out a sheet of paper, put your name on it, put the date on it, and I'm either going to pick it up or I'm not going to pick it up, depending on if you have your homework. If you have your homework, write down your name on a sheet of paper. While I'm walking around, I'd like for you to work through the following integral. And then after you've tried that, if you get it, I want you to work this one. Okay, these two problems, the basic substitution here, or let me say this. What we have in this general integral is a constant d divided by a linear expression, right? ax plus b is linear. Anytime we have an integral where we have a constant over a linear expression, it's almost just a cookie cutter answer, almost like a formula. And that's what the second one was. It was to come up with a formula for us. So I'm going to do the second one instead of the first one. The substitution I would make is u is ax plus b. The derivative of that is what? Just a dx. I have dx by itself, so I need that dx by itself. So I get rid of the a by doing 1 over a on both sides. 1 over a du is what will replace dx. And then I'm going to replace ax plus b right there with what? With u. And then the d on top, just take it out. So we have the new integral becomes d is out, integral 1 over the u now, and then, where's my 1 over a? Why don't we bring that a out, right? The 1 over a comes out of the integral. It's a constant, so d over a. What's the antiderivative of 1 over u? ln. So we have natural log u plus a constant. So this is d over a, natural log. Replace u with ax plus b plus c. There it is. Oh. The moral of the story is that anytime we have a linear expression in the denominator and up top is a constant, the integral is automatic almost. Like, what's the antiderivative of 3 over pi x plus 7? All right, that's all. You can either memorize the formula or you can understand what's happening. No matter what, you shouldn't be going through and doing a substitution, and it should just go from this integral to that line right there. That's where you should be by the next test, I should say. All right, any questions? Okay, what I've decided to do today with the next section, partial fractions, is I want to work through the problems in the book, the examples in the book. I realize everyone can read the examples themselves and everything else, but they leave some details out that I think are important. So I'm going to be working almost linearly through the book today. And then my lectures from last semester, I have other examples you can go look at if you want. First things first, though, we need to establish what partial fractions are, what the process is. So I'm going to start out with this expression here. Let's say we have 4 over x minus 1 plus 3 over x, plus 8. No integral, okay? You don't see an integral up there, right? This is algebra, complete algebra, all right? We have 2 fractions, don't we? Yes? we can add two fractions together if we have a common denominator. So the common denominator here, I would need to put an x plus 8 on top and bottom here. And then what would I need on the other one? X minus 1, top and bottom. And then you would multiply this through. So you would do your 4 through. You do your 3 through on the other one. And on the bottoms, you would have your common denominator, right? That first multiplication through, I get 4x plus 32 over my common denominator. I'm going to actually multiply out. So I took the 8 plus x, or sorry, x plus 8 times x minus 1, and I went and distributed that out and put it together, right? Okay. This is this. Then we have plus 3x minus 3 over that same denominator. And now you can put them together. So you just add up the numerators. 4x plus 32 plus 3x minus 3 would give us what? 7x plus 29 over x squared plus 7x minus 8. Right? Right. No question. So let me write underneath this. This is equivalent to 4 over x minus 1 plus 3 over x plus 8. These two expressions, the blue one and the black one here, are the same expression, right? They're the same things, just written different ways. So if I wanted to find the antiderivative, right, if I came in here and I said on that top one, I wanted the integral of that one, dx, right? It would be the same as taking the integral of this one, dx, wouldn't it? Which one would be easier? It looks like the one on the bottom, right? Because isn't that what we just came up with that formula for? So what would the antiderivative of this bottom one be? 4 ln x minus 1 plus 3 ln x plus 8 plus c. We're done, right? So that bottom integral is nice, easy to do, relatively speaking. But the one on top, the blue one, is harder. But we know that the blue turns into the black. We just turned the black into the blue, didn't we? We need to go from blue to black, not black to blue. So how do you go from blue to black? Partial fractions. And that's why I said this is a topic from pre-cal, but I will somewhat present it in a way that maybe you haven't seen it in a long time or something. All right, so the big question now is, how do you take something like this and turn it into this? How do you go there? How do you do that? So we'll start a new page, all right? Let's take, what was it, 7x plus 29 over x squared. Was it plus 7x minus 8? Now we're going to have a set of steps, all right? We're going to have a process, but let's just think about it first. The first thing we'll do is factor the denominator. Okay, so let's factor the denominator. 7x plus 29 over x minus 1 times x plus 8, or you could do it x plus 8 times x minus 1. Once you have factored it into these two linear factors, right? These are linear factors. Each one is linear, x minus 1, x plus 8. Then what we do is we say to ourselves, look, I know that this must be equal to one of those linear factors underneath something plus the other linear factor. I know it has to turn to something like that. What I don't know right now, by just looking, is what's on top, right? I don't know what the top of x minus 1 is. I don't know what the top of x plus 8 is. I mean, I do because we just came from this problem. What should our answer be? If I go back to that previous page, it should be a 4 over the x minus 1 and a 3 over the x plus 8. But we need to figure that out. So what I do is I call this up here A, capital A, and call this B. And look at this equation. I want those two to be equal to each other, right? And whenever you have an equation, you're allowed to multiply both sides of an equation by anything you want, right? So I'm going to multiply both sides of this by the LCD. What's the least common denominator of all those denominators? X minus 1 times x plus 8. So I'm going to multiply the left side here by x minus 1 times x plus 8. And get rid of my box here. And then I'm going to do the same thing on the other side. X minus 1 times x plus 8. What will happen on the left side? It'll be just the numerator, right? 7x plus 29 equals. On the right side, when I take this x minus 1 times x plus 8 and I distribute it through here, the x minus 1's cancel. I'm left with the a and x plus 8 next to it. When I take that x minus 1 times x plus 8 and distribute it to this one, the x plus 8's cancel, and you're left with what? B times x minus 1. Any questions? I'm trying to get my left side to equal my right side. There are two approaches to this. At this point, there are two approaches. There's the quick approach that doesn't always work, and then there's the long approach that does work, but usually requires we pull out our calculator and do something. Usually, all right? So I'm going to show you the quick approach. I suggest you always try the quick approach until it doesn't work, and then at that point, you try something else. So what is it that I'm trying to find? Someone remind me what it is I'm trying to find. Quick approach. I'm trying to find A and B. So if I'm trying to find A, let's say I'm trying to find A right now, wouldn't it be nice if that B wasn't even around? If that whole B term over there was just gone? How can I get rid of the B term completely? Yeah, if I let x be 1, right, won't that 1 minus 1 be 0? And it would kill off the B term? So you get to use a little bit of what I call the God complex here. You get to let something be whatever you want it to be. All right? I'm letting x be 1. And if I let x be 1, rewrite the entire equation I just highlighted there. The entire thing. Because that equation has to be true, right? And if you replace x with 1, you got to replace every x in the equation with 1. So let's do it. What do you get? 7 times 1 plus 29 equals a times 1 plus 8. I'm writing it out in a lot of detail. I won't do this next time. Right? That's replacing all my x's with 1s. This b term's gone because that's b times 0. 7 plus 29 is 36. 1 plus 8 is 9. A times 9 is 9a. Can you solve that for a? Divide both sides by 9. A is 4. Yep. So I have a. Does that match up to what we said a should be? Okay. Now let's go get b. So how are we going to get b? Yeah, now you go back up to your equation up there. You say, how can I wipe out the a? Well, I can let x be something else now. Negative 8. So you get your little God complex again. Let x be negative 8. Everyone understand why I'm choosing negative 8? So it'll equal 0, right? Pardon me? Wait. What do you mean? What? Yes. Well, all I know is when x is 1, a is 4. Right? When x was 1, it turns out my equation turns into an equation with only one variable in it, which is a, and so I solve for a, I get 4. But I can't continue to use that to get b because b is already gone. But by choosing x to be negative 8, I should be able to now get what b is. So you plug in, let's 7 times negative 8 plus 29 equals a, let's see, negative 8 plus 8 plus b times negative 8 minus 1. Did I get that all plugged in right? 7 times negative 8, negative 56 plus 29, negative 27. The a term this time cancels, which is good. And b, I have b times negative 9, which is negative 9b. So that means b is what? Positive 3. Yes?
And these are the numbers that were in the equation.
That's right. That's right. So I have done what I set out to do, right? I have found a way to take that original expression and break it into two other expressions. So let me put this all together now into a final problem. Let's suppose that we're sitting here with an example now, and we're given the integral 7x, was it minus 29? Or plus 29 over x squared plus 7x minus 8 dx. Let's say we had that problem to start. What you would do is you would take it and you would do partial fraction decomposition on the inside, right? Break that down to be two things separated. We just did that on this, separate problem, separate work, everything got, let x be 1, let x be negative 8. We got our a and b. Okay, so this integral actually turns out to be 4 over x minus 1 plus 3 over x plus 8, right? Is that correct? And now I can do what we just did right at the beginning of class and what we just talked about. 4 natural log x minus 1 plus 3 natural log x plus 8 plus c. That's it. Does that make sense? No questions? Okay, I'm going to show you. Oh, hey, there's my final from Cal 2. Where's the lectures? There it is. Okay. Let's get to a more formal process here, all right, when it comes to partial fractions. I don't write this all down, okay, because you don't have time for it. Partial fractions. Anytime you have an integral where you have a polynomial divided by a polynomial, like we just had, 7x plus 29, that's a polynomial divided by a quadratic, which is a polynomial. Anytime you have that, you can try partial fractions. Try partial fractions. So here's what you do first. If the degree of the numerator, what's the degree? Highest power, right? If the highest power of the numerator is bigger than or equal to the highest power denominator, the first thing you have to do is long division, which we haven't even looked at this yet, that part, okay? If we take care of that step, the next step is factor denominator. Wasn't that what I did there a second ago? I took the x squared plus 7x minus 8, and we factored it, right? And then apply partial fractions. And now I have this table that's just going to look terrible. Look at the first top left corner of this table. It says for each factor in the denominator. So remember our factors were x minus 1 and x plus 8, right? So x for each one of those, the ax plus b right here is like a linear factor. It's like the x minus 1. For each one of those, I put a constant over it, right? So I had put a over x minus 1. But then I had another linear factor, x plus 8, so I put another b over that, right? Does that table make sense? For each linear factor, you have to create one of those in your breakdown. Yes? All right. We haven't done any of this, so let's just wait. Okay? We'll get to this later. But the set of steps is what I wanted you to see there, because I'm going to present you now with a new problem. Let me see here. You know what? I'm going to copy this page. Copy. I'll copy it so that this appears in your notes if you print these out. How do I paste? Hey, worked. Okay, here we go. Let's take a look at this integral. X cubed plus x over x minus 1 dx. Yeah, so when I look at this, I might be thinking, okay, do I see a basic substitution? Not really. Integration by parts? Not really. Trig substitution? Well, with trig substitution, we were always looking for like a squared minus x squared, or x squared minus a squared, or a squared plus x squared, right? So now you see you kind of have to go through your mental Rolodex of what you can do with integrals. And so you get to this and you're like, all right, well, I do have a polynomial divided by a polynomial, so maybe partial fractions will work. I now check to see what the degree of the numerator is. It's 3. The degree of the denominator is 1. When that happens, you must do long division. So let's see if we remember long division. Long division works like this. I'm going to take x cubed plus x and divide it by x minus 1. Do y'all agree with that? No? Yeah, it depends on how you learned it, but yes, you could do that. Like sitting, I always just leave spaces, but yeah, there's actually a 0x squared there, and then plus a constant if you went out there, depending on how you learned division. It may have been a while since you did long division, especially with like polynomials like this. So I'll just remind you real quick. What you do, make sure everything's in descending order, highest power of x down. And then you look at the x here, you ask yourself, what do I have to multiply x by to get that x cubed? So what do you multiply x by to get x cubed? X squared. So I put that above the x squared here on the top of my division box. And now you actually multiply x squared times your divisor. So that means I'm multiplying x squared times x and x squared times negative 1. So x squared times x is what? X cubed, I put that under here. X squared times negative 1 is negative x squared. Now what we do with division is like we did when we were in grade school, is we come through and we change the sign. So this becomes negative and then plus, and then goes straight down. The x cubes cancel, don't they? Then I have nothing plus x squared, which is x squared, and then I still have the plus x, and then the nothing, right? Questions? Next step is to ask myself again, what do I multiply x by, the green x, to get now x squared? X, right? So I put plus x on the top. And I multiply that through again. I go x times x and x times negative 1. So x times x is x squared. And x times negative 1 is negative x. Come through. Change the signs, minus and plus. And go ahead and add down. What would you get? 2x. And we ask ourselves again, what do you multiply x by to get this time 2x? 2 plus 2. Yeah, I don't know why it's done that. Plus 2. 2 times x is 2x. 2 times negative 1 is negative 2. Come through. Change signs. Add down. What do you get? 2. Now I ask myself, what do I multiply x by to get 2? Well, as soon as the power out here becomes larger than the power here, you can stop. So we can't get x to become 2, so 2 is like the remainder. But we don't write R2, right? That's way, way a long time ago. Okay? What we do is we say plus the remainder, which is 2, over the divisor, which is what? X minus 1. So this integral, after long division, turns into all that, doesn't it? So I'm going to rewrite my integral. It's x squared plus x plus 2 plus 2 over x minus 1 dx. And can you integrate that term by term? Yes. It is 1/3 x cubed plus 1/2 x squared plus 2x plus what? 2 natural log x minus 1 plus c. What do you think? Sorry, that got a little small. But see, what I did by the long division, I was able to just take that, rewrite it in a different way where I could just integrate each term. I'm not real big on stopping class for something, but I am because I want to show you all something. Let me pause my video. Someone please remind me.